Welcome back everyone. In this lecture we will actually study the isometric matrix of R2. So, first let us recall some basic results about R2. So, R2 is a two dimensional plane. Okay. As a set, it is a Cartesian product of two copies of real lines. So, we use this x comma y to denote the elements of this R2. So, where x and y both comes from R. So, pictorially, so we draw this y axis as well as x axis. So, here you have x axis and here you have y axis. So, then any given point is actually denoted by this tuple x comma y, where x actually measures the distance from origin to this so origin to the projection of x comma y on this x axis. Similarly, this y measures the distance between origin to the projection of x y on y axis. So, this is your y, this distance, and this distance is your x. So, now we often actually identify R2 with the complex plane. Okay, that way we can actually do some algebra. So, we often identify R2 with the complex plane. So, complex plane again you write instead of the pair x comma y, you write x plus I y, where x comma y comes from R, where I is the imaginary number whose square we assume to be minus 1. Okay, so, this is our two dimensional plane R2. So, now we have a standard inner product on R2. So, that is something we will fix, because we want to study about the isometries of this R2. So, isometries are nothing but maps from R2 to R2 that preserves actually distance. So, because we are going to talk about distance, we need this inner product. So, what is this inner product? So, the inner product is defined as follows. So, for u comma v in R2, if you write u equal to some a comma b and v equal to some c comma d, so then the standard inner product, which is denoted by u dot v. So, this is also called dot product sometimes. So, this is either dot product or inner product, standard inner product. So, this is defined to be you first multiply in the x coordinate term, which is AC, then you add BD. So, this is your definition of dot product. So, once we have this dot product, then we can actually immediately define a distance between 2 points using the norm that comes from the dot product. So, what is the norm? So, the norm of any vector is defined to be square root of this a square plus b square. So, which is nothing but the square root of u dot u. So, using the inner product, you define this norm for any u in R2. So, now once you have this norm, so this is the standard norm. So, we have the standard distance from u comma v, so which is just the norm u minus v. So, in terms of this a, b and c, d, the coordinates, you can see that this is nothing but the square root of a minus c square plus b minus d square. Okay. So, this is the distance on R2. So, now there are many basic properties of the distance, I believe all of you know. For example, distance satisfy triangle inequality and so on. So, most important thing is the distance between u comma v is same as distance between v comma u, and distance between u comma u, that must be 0. And if you take 3 points u v w, then the distance between u v plus distance between v w must be less than or equal to the distance between u comma w. So, these 3 important properties of distance are satisfied by this formula. Okay, now we have distance, we have inner product on R2. Now, with respect to that, we want to study some maps that are preserving these properties. Okay, so what do you mean by that? Okay, so let me define what is an isometry. Okay, it is a very important object studied in geometric group theory. So, an isometry is a map, an isometry of R2 is a map, let us call it H, from R2 to R2. So, satisfying the following properties, satisfying the following property that if you take the distance between H of u and H of v, that is the distance between the images of u and v must be same as the distance between u v, and this should be true for all u comma v in R2. Okay. So, basically what is an isometry? It is a map from R to R2, R2 to R2 that preserves distance between any two given points. Okay. So, this is the definition. So, now we need another definition of maps, those are called linear maps. Okay. So, because these isometries they have very close relationship with linear maps. So, we need that definition. So, I am just going to recall what is a linear map. Okay. So, a linear map from R2 to R2, okay, which is denoted by T, is a map satisfying the following condition. Okay. Is a map from R2 to R2 satisfying the following conditions. The first condition is T is linear in the given vectors u and v. T of u plus v should be T of u plus T of v for all u comma v in R2. So, then if you take, it should be R linear. Okay. One can call it linear or R linear. So, both are synonyms. So, it is R linear whenever you multiply by some constant, some c times u, then the c comes out. So, gives you c times T of u for all c in R and u in R2. Okay. So, the linear maps are well studied in linear algebra, but even if you haven't done any linear algebra course, you can actually just work out linear maps that are defined on R2. Okay. So, linear maps they are actually defined using these two properties. So, now I will recall some of the elementary facts about these linear maps. So, those properties are easy to verify. I will leave it to you to check. Okay. So, what is the most important property? Like you have the standard basis of R2 which we denoted by E1 and E2. So, E1 is the first standard basis vector 1 comma 0 and E2 is the second one which is 0 comma 1. So, these are two vectors in R2. So, this is called actually standard basis of R2. So, this is the standard basis of R2. So, what is the meaning of that? So, any given vector, okay, any given vector V in R2 can be written uniquely as linear combination of this E1 and E2. So, that means there exist unique x and y tuple from R such that this V is written as x E1 plus y E2. So, those unique tuples you can see that they are the x coordinates and y coordinates of this V. Okay. So, this is the most important property of this basis E1 E2. So, now so given a linear map what one can actually say. So, this linear map is uniquely determined by its action on the basis. Okay. T is uniquely determined by its action on this E1 and E2. So, what is the meaning of that? Once you know what is T of E1 and T of E2, then you can write down what is T of V for any V. Okay. So, why it is true? Because if you start with V, then you know that there exists x and y such that V equal to x E1 plus y E2. So, in particularly if you write T of V using the linearity, you can see that this is exactly equal to x T of E1 plus y T of E2. So, in particularly if you know what is T of E1 and T of E2, then you are able to write down what is T of V. So, that is what this statement says. Okay. So, now there are various bases that are available in R2. So, in particularly we have the standard inner product which is dot product. So, with respect to also we can actually talk about some special kind of bases in R2. So, they are called orthonormal bases. Okay. So, what is orthonormal basis? So, some u comma v, it is said to be orthonormal basis. It is a basis of R2 and satisfy the following conditions. Okay. So, let us say there are two vectors u v of R2. So, this is said to be orthonormal basis if both of them are unit vectors. So, that means the norm u, norm v both are 1, and the second condition is whenever you have you take the inner product between u and v. So, that should be 0. Actually, once you assume that u is not multiple of v, and then if it satisfies these two conditions, then you can actually immediately prove that u and v that must form a basis of R2. But anyway, using this property, what one can conclude that any given vector w of R2, you can write this w some unique way using u and v. Okay. So, this w you want to let us say write C1 u plus C2 v for some C1 C2 in R. So, note that u and v that form a basis of R2. So, in particularly given any w in R2, you can write w as linear combination of this u comma v. So, now if you just work it out using this orthonormal property of this basis vectors, you can see that the C1 and C2 can be recovered from this inner product. So, if you take the inner product w dot u, then you can see that this is exactly equal to C1 u dot u plus C2 v dot u, but u dot v is same as v dot u, which is 0. So, in particularly what you get w dot u is exactly C1 and u dot u is 1 because the norm u is 1. So, norm u square which is u dot u, which is also 1. Similarly, you can see that w dot v that is equal to C2. So, in particularly once you have orthonormal basis, then w can be written as w dot u times u plus w dot v times v. So, this unique expression you can get using orthonormal basis. Okay. So, this is very important observation. This will be used later to understand the isometries that actually maps origin to origin. Okay. So, these are some basic terminologies that you see in basic linear algebra. So, now as I promised, we want to understand all isometries of this R2. So, let us see like what are all the isometries that we have in R2. So, first we begin with some examples, and then later we will see that more or less those examples exhaust all possible isometries. So, one can do whatever I am doing now using purely geometry. Okay. But since this is a course in algebra, so let us do everything algebraically. Then later we will actually associate with geometry and then see what happens there. Okay. So, first of all, we want to understand given isometry. So, by definition, note that isometry is just a map that preserves distance. So, in particularly, all you can say this isometry is nothing but injective map. Okay, whenever you have 2 points, okay, uv. So, if the distance between u and v are 0, then they are same. So, then that would immediately force that the distance between h of u and h of v, that must be 0. So, that will imply that h of u equal to h of v, and if you assume h of u equal to h of v, that would imply immediately u equal to v. So, that means all you can say. Okay. So, if you start with h is isometry from R2 to R2 is an isometry. So, then from the definition, it is immediate that H is an injective map. Okay. But if you see some examples, then you can easily see that many isometries that we know, they are all actually both injective as well as surjective. So, they are indeed bijective maps. So, that is what one would like to actually see. So, we want to actually understand this set of isometries, which we denoted by ISO M of R2. Okay. So, ultimately what we want to prove that these isometries of R2 that form a group. If you want to prove something like that, then first you need to like find out, okay, given isometry, inverse of isometry. If you want to talk about inverse of an isometry, then you need to first prove that given isometry must be actually bijective. Okay. So, because it is invertible. So, let us see like why that actually comes for free from our analysis. But if you attempt to do that without actually using the classification of isometries, then it becomes much harder. Okay, so let's understand given isometry how it looks. Okay, before that, let's see some examples. So, identity is obviously an isometry, and then if you take plus or minus identity, that also will be an isometry. So, identity is nothing but identity of x equal to x for all x in R2. So, this is your identity map. Then both identity and minus identity, they are actually isometries. So, now from the geometry, it is very clear that if you take a reflection with respect to any line, that must be isometric. Okay, reflection with respect to any line must be isometric. So, how it looks like, you draw some line, okay, let us say this is the line L, then you reflect with respect to this L. So, that means all the points lie on that line, they all fixed. Okay. Then if you take some point which is not on the line, then you use this L as this mirror symmetry. Okay. So, then you project using this. Okay. Basically what you do, you draw this orthogonal line, okay, which is orthogonal to L, that connects this dot. Okay. Basically you draw this line, so which is orthogonal, and it's actually connects this V and this line L. Then you extend that to further with the same distance that you have here. So, then whatever you get the end point of that other side, so that is your reflection with respect to this. So, S L of V. So, this is the image of the reflection with respect to capital N. Image of V Okay, so it's now very clear that, so given this reflection, you can see it must be injective as well as surjective. Okay, and the inverse of this reflection is itself, because this is order 2 element. Okay, so because if you reflect V to SL of V, then if you reflect it back, you will get V. Okay, so this is basically this SL inverse is nothing but SL. So, this is an isometry which is invertible. So, now let us look at another geometric example. Okay, again it is very motivated example. So, this is actually a rotation. So, again rotation, now again with respect to any point. So, with respect to a given point. So, this is also an isometry, okay, that is very clear. So, you plot the point, you call it P, then what you do, you rotate the entire plane with respect to this point P. For example, if you take another point, call it V, so then you draw this arrow that connects this P and V, okay. Now, if you want to, let us say, rotate some angle theta both counterclockwise as well as clockwise. So, let us say we are only talking about the rotation which is counterclockwise rotation, okay, counterclockwise rotation. So, then what happens, then if you rotate like this, so then about this angle theta, then this point V reaches to this r theta of V. So, this is your angle theta. So, this is your r theta phi. So, now you can see that of course, this rotation is depending upon the point P. Okay. So, now from the geometrical interpretation it is easy to verify. Okay. So, if you take the inverse of this rotation, so then this is exactly rotation with respect to the minus theta, okay, about the same point P. So, now it is clear that this rotation with respect to a point P, okay. So, of course, rotation with this about this counterclockwise, that is invertible isometric of R2, okay. So, this is important. So, there is another important class of isometries which come from translations. So, translations are another kind of isometries. So, what it is? So, fix some vector V in R2. So, then define this translation TV. So, which is a map from R2 to R2 such that any x goes to x plus V. Okay. So, this is your translation, and it is clear that translations are again invertible, and the inverse of the translation is just T minus V. Okay. And you can easily check translations are again distance preserving maps. So, I will leave it to you to check all the maps that I have actually written here. So, the reflections with respect to any line and rotation with respect to a given point and translations, all of them are actually isometries. They are all distance preserving maps. So, now what you can do now, you can actually compose them and then get some new kind of isometries. For example, so it will be proved later. So, if you take composition of two reflections, then what you get max is either a translation or a rotation. Okay. If you take a rotation and then compose it with rotation, then you will again get rotation. Okay. So, now if you take translation compose with translation, again you will get translation. Now, what you can do, you can compose translation with reflection. Okay. So, then you get something called glide glide reflection. Okay. So, that is the fifth kind. So, you get what is called this glide reflection. So, this is obtained from by taking translation composition with some reflection, T composition some R. For example, what it will do, so let us say you want to like reflect, okay, let us say, so this is your line of reflection, okay, let us take some object like this triangle that is sitting on this line. So, first what you want to do, you want to reflect it. So, then the reflection will go like this, and then let us say you want to translate it along this right hand side about some vector u. So, then this will just move to this here. Okay, this is called glide reflection. So first you take this triangle, reflect and then move it towards the right side. So this is the image of this triangle using this glide reflection. So one can prove that, so that will be our final result. Any given isometry of R2 will be one of them. Either it is a reflection with respect to any line, or a rotation about any point, or a translation, or a glide reflection. So these are all the only possible isometries that we can have it in R2. So for that purpose, so we will actually use some algebra to write down very explicitly how given isometry will look like, and then using that information we will prove what I promised. Okay. So towards that, so let me just give some algebraic formulas that actually explains the some of the maps that I actually written here. So you can see that this translations, they are given very algebraically, there is no issue. So given vector v, so you can assume that vector to be non-zero vector. If it is a zero vector, then you get identity map. So then x goes to x plus v is going to give you translation. Now what's about reflection? Okay. So reflection again can be obtained as follows. So if you are interested in reflection with respect to any line, then what you can do first, actually you can translate that line to line passing through origin, then you can reflect with respect to that line. So it can be written as composition of two isometries. One is the translation, another one is the reflection with respect to origin. So because of that, translation we already understand. So we will just only understand the reflection with respect to origin. Sorry, reflection with respect to a line that passes through origin. So this is something we can write it down very explicitly using algebraic formula. Of course, all isometries can be written very explicitly using algebraic formula, but as a first step towards that, we will write down this. Okay. So let's look at it geometrically what happens. So you have this xy plane. So then you have a line with respect to that you want to actually reflect. So this is, let's say, your line of reflection. So then you can see that you can choose this normal vector which is perpendicular to this. Okay. So call that vector alpha. So you can make this alpha unit. Okay. You can choose alpha such that the norm of alpha is 1, and of course you can fix one of the unit vectors, so that let's say it's there on the right side of this line. So then it's clear that this L is actually given by just alpha perp. So alpha perp is nothing but those vectors beta in R2 such that beta dot alpha is 0. Okay. So this is indeed a line which is a one dimensional subspace of this R2. So this is y axis, this is x axis, and you have this line passing through here, and you have this line given by this normal unit vector alpha. Okay. So basically L is alpha perp. So now if you take some gamma which is on this plane, and if you want to reflect it, then what you do, you reflect with respect to this line. So then basically you will be just mapping this to this S alpha of gamma. Okay. Now note that I can write this reflection with respect to this L as S alpha, because the reflection with respect to this L is uniquely determined by this chosen vector alpha. Okay. So there is a reason to actually write this as S alpha of gamma, because if you think about it, algebraically speaking, this reflection is actually a linear map. Okay. So this can be very explicitly given uh, using this formula. Okay, S alpha of gamma is exactly equal to S alpha of gamma equal to gamma minus twice gamma alpha divided by alpha alpha alpha. So, not all reflections are linear maps. Reflections, so that actually fixes this origin. So, that will be actually linear map. Okay. So, since this L is a line that passes through origin and all points on the L are fixed. So, in particularly this reflection with respect to L fixes origin. So, it must be linear. Okay. This we will prove it for any isometry that fixes origin. But anyway, now using this explicit formula, you can actually check that S alpha of gamma will be gamma if gamma comes from this alpha perp, which is L, and S alpha of alpha is going to be minus alpha. Okay. So, now you can see that this S alpha of gamma is a linear map satisfying these two conditions. So, because of these two conditions, this must define a reflection with respect to L. Okay. I will leave it to you to check it is indeed a reflection, okay, with respect to L, and it is also an isometry. Okay. So, that is something you can verify directly. Okay. So, it must in particularly it is distance preserving map. So, this is a simple exercise. I have given you very explicit formula. You can use that formula to verify this. Okay. Similar to this, rotation again about to origin, that is also easy to actually write down. So, if you assume let us say r theta is the rotation about the origin. So, this is where we want to identify r2 with c. So, then it becomes clear what is the map. So, then this rotation, counterclockwise rotation, okay, where theta you fix between 0 and 2 pi. So, this is something you fix. Then the counterclockwise rotation, counterclockwise rotation, r theta is given by r theta of z equal to z times e power I theta. So, this multiplication indeed helps to write down the formula for rotation. So, if you are interested in writing down this very explicitly, you write z equal to x plus I y, and then e power I theta, you know what it is cos theta plus I sin theta. So, in particularly r theta of x comma y can be obtained from this z times e power I theta. So, which is going to be x cos theta minus y sin theta. So, this will be the x coordinate plus I x sin theta plus y cos theta. So, this is your coordinates. So, x cos theta minus y sin theta comma x sin theta plus y cos theta. Okay. So, here is another way of writing this using matrices. If you think about it, this is exactly cos theta minus sin theta x y, and then sin theta cos theta. Okay. So, most of the books actually write this definition using this matrix they write this formula for r theta. But anyway, it just comes from this formula, like z goes to z e power I theta defines rotation about this angle theta. So, this is again using this very explicit formula, you can again check this is the rotation about the origin. So, r theta, so I will leave it to you to check. So, this is the rotation about the origin of course with the rotation with respect to theta. Okay. Okay. So, these are all some examples that very explicitly given using algebraic formulas. So, now we will use such things, and then we will later actually write down a very explicit formula for all isometries. So, I will do it in next class, maybe I will stop here. Thank you.